So we're on lecture 2. We're going to talk about molecular spectroscopy. What's the simplest molecule we can have? A diatomic molecule. 2 atoms. They come in 2 types. Homonuclear means the 2 nuclei are the same, like molecular nitrogen. Heteronuclear, they're not the same. Carbon monoxide. Big difference. This is the spectrum. So we're going to introduce the spectroscopy of diatomic molecules, recognizing our target. Our target is to understand how to do row by. That is to measure some of the things I've shown you: CO, CO2, using infrared light, and those are a combination of rotation and vibrational quantum changes. We call that row vibrational spectroscopy. But I'm going to introduce it in sequence. I'm going to talk to you about the rotational part, and then we'll add in the vibrational part together. So I'm just going to give you a quick introduction to the way we think about quantum mechanics of diatomic molecules. So there's a question about why the light interacts with these diatomic molecules, and really progress through a sequence of models. So in spectroscopy, what we do is we have a model. I like to use a mechanical model of the molecule, and then we introduce 2 or 3 rules from quantum mechanics, and we're done. But it rests on a mechanical model. Do that. And then we'll start with the simplest model, which is called a rigid rotor, which means that these 2 nuclei have a fixed length, spacing. Then we'll allow them to be slightly non-rigid, and then we'll bring in the rotational part. So remember, here's this potential energy diagram in a particular electronic state, the ground electronic state. What's the meaning of this? These horizontal lines correspond to the vibrational energies. So if you have a molecule with this amount of vibrational energy, it oscillates. This oscillating is trading potential and kinetic energy. So at this endpoint here, that's the amount of potential energy it has. When it goes down here, it's lost its potential energy and it's all kinetic and goes up here. So it oscillates in this well. We think of that. Buried, superposed on top of that are rotational energy level structures. And so if we have transitions between allowed rotational states, those transitions occur in the microwave region. They're called pure rotational change. We mostly are concerned with the combined rotation and vibrational change, which are higher energy and they occur in the infrared. So now let's imagine how the light interacts. The way you think about it is whether or not the molecule has an electric dipole. So imagine hydrogen chlorine. So that's a heteronuclear molecule, meaning that the 2 ends are different, and you can think of one of them having a slight difference in charge. So when that molecule is stretching, it's varying that electric dipole moment, and that's how you think about an antenna. So whether you're emitting light or absorbing light, when you have that oscillating electric dipole, there will be interaction with electromagnetic radiation. Bigger molecules like H2O have some of the same properties. So again, we're thinking about either absorption or emission. By the way, at equilibrium, all processes are balanced, microscopically balanced. If it can emit, it can absorb. So we think of them together. Now, on the other hand, what if this molecule is homonuclear, like nitrogen? No dipole moment. Can't interact. Doesn't have, to first order, it doesn't have a rotational or row vibrational spectrum. Now, that doesn't mean you can't study the structure of the nitrogen, but you've got to use another method. So if it's homonuclear, we rely in some cases on what's called elastic scattering. So elastic scattering is when the incident photon of frequency nu bounces off of a molecule and goes away with the same frequency. Since the photon energy is the same, that means the molecule hasn't changed. If the internal energy of the molecule is unchanged, that's called an inelastic collision. If the internal energy is changed, it's inelastic collision. So we can have Rayleigh scattering, which is responsible for the color of the sky, just due to the scattering of light off of molecules without changing the quantum state. It occurs. In that case, then the scattered light does have the same frequency as the incident light if you're using a laser. But now what are other possibilities? Another possibility is inelastic scattering. In inelastic scattering, shown down here, this incident frequency is converted to nu sub s, or nu sub as. And so it's possible by a weak process, called the Raman process, that this incident photon will be changed into emission, or emission of photons of 2 different candidate frequencies. one in which the molecule initially in quantum state n goes to m. If n goes up in energy, the molecule has gained energy, the photon must lose energy. Conservation of energy. If, on the other hand, the molecule goes from quantum state n to m, the photon, the emitted photon, has gone up in energy. Conservation of energy. And those two outcomes are called the Stokes and the anti-Stokes options. They both can occur. And that's called inelastic scattering. So it's weak, but it occurs. And you can imagine that the person who gets the credit for it is called Raman, Indian scientist. So remember, back to our elements of spectroscopy: positions, strengths, and shapes. Positions. Position is really determined by the difference between energy levels. So if we have expressions for the energy of the levels and a rule for the levels that can talk to each other, we've just computed the positions of the spectrum. So where do we get the energy levels? Quantum mechanics. We're going to just take advantage. There's a few simple rules we try to follow. The first one is we think of the internal energy. Now there's the internal energy, and then there's the energy associated with the kinetic energy of motion of the nuclei, of the center of mass. We don't talk about that. We're only talking about the internal energy, which is characterized by three types: electronic, vibrational, rotational. And we assume, this is an assumption, that these energies are independent. That the rotational energy, characterized by a quantum number J, you'll see, doesn't know what the quantum number V is. Approximation. It's a pretty good one. So now we have to recognize we're in a given electronic state, this well. We now are going to have a quantum number for vibration. We're going to call it 0, 1, 2, and a quantum number for rotation, these fine structure here. So now remember, we need to have a dipole moment. So you have to imagine in this microwave region, which means pure rotational change, imagine this carbon monoxide molecule rotating around. What does it look like? You're going to see a dipole moment that's oscillating in the vertical direction. Therefore, it will absorb and emit light at a frequency that corresponds to this rotational frequency. So if you imagine this dipole moment kind of oscillating between down, up, think of it as an associated electric field, or the dipole moment itself. That's the product of the that's the X component. Excuse me. Therefore, it'll be microwave active. But some molecules are microwave inactive. For example, these homonuclear ones, they do not have microwave spectra. The quantum states are there. You just can't see it absorb or emit light. Now we're thinking about in the infrared. The infrared is associated with stretching motion. So now we have our carbon monoxide molecule. Now we're thinking only about the axial extension of the nuclear spacing. This is a little easier to follow. So obviously there's an oscillating electric dipole in this direction. So we can think of it this way. And if you think about it, it's sinusoidal. So that means that this carbon monoxide will be infrared active. Now, there are some vibrations in molecules that are infrared inactive. So here's a molecule CO2, which we'll find has some motions which are active and some motions which are inactive. It has multiple motions. In this case of this heteronuclear diatomic molecule, there's only one vibrational motion. In bigger molecules, we'll see there's more vibrational motions. And there'll be a combination of infrared active and infrared inactive. Okay, now the spacing of the rotations is small compared to that of vibrations, compared to that of electronics. So that tells you already where the spectra are going to be. The rotational spectra is typically in the microwave region. This is typically in the infrared region. This is typically in the visible and UV region. So as you go shorter and shorter in wavelength, the energy of the photons goes higher and higher and higher, corresponding to these energy differences. And so far, everything we're talking about is going to lead us to a discrete, line-separated spectrum. So we're going to recognize that we want rho vibration, but we're going to talk about rotation first. So we introduce this first, and we use the simplest model, which is called the rigid rotor. Then we bring in the vibration, and we're going to characterize that by what's called a simple harmonic oscillator. And we relax that assumption slightly, and it becomes a non-rigid rotor and slightly anharmonic, and that's where we end up right here. But we can get off to a very good start with these very simple models, rigid rotor and a simple harmonic oscillator. So we're going to look first at rotation. So if you had a course in mechanics, it's really a mechanics problem. We have two masses, and imagine that they're lying on a frictionless plane. And you're asked some properties of this mechanical system. You know the mass of this nucleus. You know the mass of this other nucleus. You may or may not know the separation distance. But in a mechanics problem, the first thing you do is you find the center of mass. You find the center of mass, which is somewhere here. And then you say, well, we're going to worry about the rotational motion of this system. So it's on a frictionless plane. So you find the center of mass, and then you make a perpendicular axis. And then you imagine the rotation about that axis on this frictionless plane. Now take the frictionless plane apart. This system, any system like this, once you find the center of mass and you have found a so-called unique axis, in a mechanics problem, you can find the three principal axes. There's a unique set of principal axes about which you can characterize the motions. In spectroscopy, we find the unique axis is the one that's unique is along the, it connects the nuclei. That's called, we're going to call that the A axis. The perpendicular axis is called the B axis. And then because here, there's a third axis, which is degenerate with the first one. So you have to imagine that the system can rotate about all three of these axes. You find the center of mass just by mass balance. And by the way, these distances we're talking about are of the order of 10 to the minus 8 centimeters. We assume point masses. We recognize that the diameters of these nuclei are extremely small numbers, like of order of 10 to the minus 13 centimeter, which is very small compared to the typical spacing between these nuclei of about 10 to the minus 8. Now we assume that that distance is fixed, and we're going to let it rotate. That's called a rigid rotor model. Relax that later. So in a mechanics problem, you find the center of mass, you find the moment of inertia. The moment of inertia would be the summation of the m sub I Ri squared about the center of mass. And we're now talking about the rotation about what I'm going to call the B axis, or the C axis. So it's the summation of the m sub I, of which there's two, Ri squared. That would be the distance from the center of mass. You can convert this two-body problem into a one-body problem by using what's called the reduced mass. So you replace this system here with mu Re squared, where Re is the spacing. And mu is called the reduced mass. It's the product divided by the sum. So now that converts a two-body mechanics problem to a single-point mass problem about the center of mass. Now, we've gone about as far as we can go with the solid mechanics approach to this microscopic problem. We have to introduce quantum mechanics. Quantum mechanics tells us that the angular momentum is quantized. The product of the moment of inertia and the angular rotational speed is quantized. We just accept it. And it only can exist in certain allowed states where J is an integer, starts at 0, 1, 2, 3, 4. And H is Planck's constant. We often write H bar as H over 2 pi. So Planck's constant, square root of Jj plus 1, those are the only allowed energy states of this microscopic system. So the only difference between our mechanical engineering system and this one is that we can only have discrete values of energy. You can't have a continuous distribution. We accept it. Now, we now proceed to energy because we want to get the difference in energy levels. So we take the rotational energy, which is 1/2 I omega squared, do a little algebra, and we find that the allowed rotational energies are obviously going to be quantized. And the rotational energy is allowed to be J plus 1, H squared over 8 pi squared I. Interesting. Look at that. Rotational energy depends upon a number, 0, 1, 2, 3, 4, 5. Planck's constant, pi is a constant, I. But once I have the moment of inertia, I know the infrared, I know the rotational spectrum. Depends only on the moment of inertia. Depends only on the masses and the spacing. So if you know those, calculate it, you got the moment of inertia, you've just calculated the allowed rotational energies. Now, in rotational spectroscopy, convention is that you write these energies as a function of J. These are the rotational energies, but we write it as a function of J. When you do that, rotational energy, you retain the JJ plus 1, but you can lump all of the other constants together into what's called the rotational constant B, and which will depend only on constants and the moment of inertia. So once you have the moment of inertia, you know the rotational constant B. It's a number. It's a number, which is different for every molecule. Now, at this point, I'm talking about homonuclear, heteronuclear. It's all the same. We're not talking yet about the absorption or emission of light. So B is the rotational constant, and it'll have units. Now, in spectroscopy, we use units of centimeters minus 1. They're called wave numbers. It's 1 over lambda. That's called the rotational constant. It's specific to that molecule. So basically, energy in wave numbers is energy in joules divided by hc. That's in your notes. Now, you might say, where did we get some of this information? Well, it basically comes back to quantum mechanics. Quantum mechanics, you solve what's called Schrodinger's equation, because so far I've just told you we accept from quantum mechanics that the angular momentum is quantized, which means that the energies are quantized. We need something more. We need to know which transitions are allowed, which J's can talk to each other. So we have to go back to quantum mechanics, and we call that the transition probability. You do this for a rigid rotor, and it might take a quarter course in spectroscopy at Stanford. You'd be able to do this after 1 quarter. You would find that delta J can only be plus or minus 1. The result of the rigid rotor in a rigorous solution with quantum mechanics is that J can only change by 1 in emission or absorption. Pretty simple. These are the wave functions, and that's called the complex conjugate, and it all comes back to understanding this dipole moment. So if there's no dipole moment, there's no transition probability. So we combine the angular momentum is quantized, that leads to the energy is quantized, introduce the quantum numbers J, introduce the transition probabilities, delta J is plus or minus 1, we're basically done. So the selection rules are written this way. Delta J, which I define to be the difference between the upper state and the lower state, is always 1. This way, whether it's emission or absorption, doesn't make any difference. It's J upper minus J lower is 1. Not everybody does it this way, but this is the way I do it. The delta J is 1. That's all that can happen. So now, since f of J is bjj plus 1, I can solve for the energy of a transition between 0 and 1. That'd be the energy difference between J of 1 and J of 0, and what do I get? 2b. Energy difference between J of 0 and 1 is 2b. So let's look at this. Here's the diagram. So here's our expression for energy. Here's the energies, F. If I'm in J of 0, the energy is 0. If I'm in J of 1, I have an energy of 2b. If I'm J of 2, I have an energy of 6b. If I'm J of 3, I have an energy of 12b. Those are the allowed energy levels, whether it's homonuclear or heteronuclear, it doesn't make any difference. Those are the energy levels. It's only when I impose that it has to be heteronuclear to have an absorption probability that I take to calculate the spectrum. So for a given J, I get a given specific F, and I take what's called the first difference. That would be the differences between these quantum states. 2b, now this one's 4b. What does that mean? That means if I looked at the spectrum, I should see lines at 2b, 4b, and 6b. Not the same place because of the energy spacing. That corresponds to, then that leads us to what's called the second difference. If you take the difference between these numbers, you get a constant number. And you'll see what that means in a minute. There'll be a line every 2b in the spectrum. So in general, you can solve for the energy differences of any transition, J double prime to J prime, and you'll get this simple answer, which is that the frequencies are 2b J double prime plus 1. So if you tell me J double prime is 0, I get 2b. If J double prime is 1, I get 4b, etc. So solid mechanics, mechanical model, couple results from quantum mechanics. I've already got the positions of the lines. In terms of the moment of inertia, not that hard to do. That's an approximation. The rigid rotor is not perfect, but it's pretty good. So now we can look at the absorption spectrum. And we're going to see lines at 2B, 4B, 6B. So now let's imagine that we'll plot this as, here's the transmission, fractional transmission as a function of frequency, which I've divided by 2B's to make it simple. So here's J of 0, 1, 2, 3. So there's a line at, for J of 0, 1, 2, 3, 4, 5. And the transmission would be dipping at each one of these things, if it's heteronuclear. Got it. It's not that complicated. And if you put in some typical units where B is approximately 2 wave numbers, that means that that first transition has a wavelength of 2.5 millimeters, which by definition means you're in the microwave region. So all of these transitions would be in the microwave. So the people who do rotational spectroscopy are microwave engineers. Different kind of systems than we do. We're not going to be doing that, but we need this information to go into our rho vibrational. This only works now for heteronuclear. Homonuclear molecules have the same energy structure, we just can't see it by emission or absorption of light. We have to resort to something else like Raman spectroscopy. Now you might say, what is this good for? Well, if you measure the spectrum, let's say you measure the spectrum of CO, and you measure the spacing of the lines, which is 2B, what have you just determined? You just determined the moment of inertia. If you knew that it's carbon monoxide, C12, or 16, if you took those masses, you just determined the internuclear spacing. That's all it depends on. So you can see that some people would use spectroscopy to study the structure and energy level structure and the details of molecules. We're more interested in monitoring these molecules, but we have to understand the spectra to do that. So the spacing would tell us immediately what the moment of inertia is, which would tell us the value of RE. We do this in my lab class. Just take some simple equipment. We measure the spacing of the lines. We see a number of about 1.92. We don't measure it to that many significant figures. We measure it maybe to 4. That implies a length of 1.128227 angstroms. Now we're talking about distances of 10 to the minus 16 meters. So the spacing. So you can measure frequencies pretty accurately. So if you measure the frequency of these lines, take 2B, you've immediately found out something about this molecule, internuclear spacing. Now, I have an approximation I use. It's a crude approximation. It says that the absorption or emission is mostly dependent only on the relative populations in J. So in other words, the Boltzmann distribution immediately will tell me what the spectrum, the strength of the lines will be. So remember from the Boltzmann distribution, the fractional population in J is so-called degeneracy, which for rotation is 2J plus 1, e to the minus energy over KT divided by Q. Turns out that if you sum over all the allowed states, it comes back to something that's this T over theta R. Theta R is going to be proportional to B. So there's a very simple relationship for the fractional population in J. In terms of J, the energy of that state, and the rotational partition function. So the degeneracy 2J plus 1, you might wonder where that comes from. That comes from, we have to accept quantum mechanics for that one again. Quantum mechanics says that even if once you tell me J, if there is a field present in the gas system, then the allowed orientations of my molecule there are 2J plus 1 possibilities to satisfy quantum mechanics. Now, since we generally don't have an applied field in the problem, we just have to count this as this is the number of states which have the same energy. That's the number of states that have the same energy. We can't distinguish those, so we have to count them in the statistics. Statistical mechanics is all about statistics. In quantum mechanics, you have to keep track of the statistics. Now the partition function is the sum over states. Sum over all of the fractional distributions, and you get this partition function, which is KT over HCB. And this has to do with the orientation. So this has to do with how many ways can I turn this and it looks the same. So for CO, when I turn it around, it looks different. But nitrogen, when I turn it, it looks the same. So you have to have a sigma of 2, all about statistics. So That's the number of ways of rotating it to achieve the same apparent orientation. 1 if it's microwave active because it must be heteronuclear. So for CO it would be 1, for nitrogen it would be 2. So why do we care? This is all about statistics, the population fractions and level J. Keep track of this. Now, okay, here's the definition of theta. So if you take B and you multiply it by HC over K, so that we can put it up here, that has units of kelvins. That way we can end up with kelvins and kelvins. So there's a characteristic temperature for the rotational energy. And that number, HC over K, I drill into my students, is 1.44. 1.44 kelvins per wave number. So if I tell you that B is 2, which is approximately correct, 2 times 1.44 is 2.88. So in other words, the characteristic temperature associated with rotational motions of CO is 2.8 degrees Kelvin. And since we're typically interested in room temperature or higher, the spacing of these rotational energy levels is small compared to room temperature and higher. So that is a simplification that we sometimes use. So the rotational spacing is measured in kelvins is small. The vibrational temperature measured in kelvins is big. For carbon monoxide, it's about 2,900 degrees Kelvin. So we kind of relate temperature and energy to get a feel for how we can distribute these molecules. Okay, now about intensity. Remember, we're all about positions, strengths or intensities, and shapes. Rotational temperature, okay, 1.44, it's worth remembering. So here's some representative diatomic species. Here's their characteristic temperatures. Notice when you get to something like chlorine, why does chlorine have such a small number? Well, what's B? Inverse with moment of inertia. So the moment of inertia is bigger because of higher masses. You're going to have a smaller B. So this all has to do with the molecular structure. So for oxygen, N2, NO, they're about the same. Many other molecules can be quite different. Remember, this is the Boltzmann fraction now that we can write. And now you can ask, which rotational state has the highest population? You can take the derivative of this with respect to J and set it equal to 0 to find the peak, and you would find that it's something like this. It's something like T over 2 theta R. So you might find that J max at room temperature, that J max for, say, CO might be 9 or something like that. This is kind of telling you how many rotational states you have to think about on the temperature. You go very high temperatures, what happens? The temperature goes up, the peak of the Boltzmann distribution goes up. And so the quantum states get distributed to higher and higher and higher J. They're all populated. The question is, where's the peak? Okay, now let's see. What about isotopic substitution? So let's say we know this. We know that B is H over 8 pi squared IC. What happens if you change to an isotope? What happens if you go from carbon 12 O16 to carbon 13 O16? You change the masses. You change the moment of inertia. Have you changed the internuclear spacing? No, because the internuclear spacing is set by electrical forces, not independent of the masses. Therefore, you can play a trick. You can recognize that the ratio of these B's, because if we take the known masses, is something like this. It's the ratio of the B's. What does that mean? That means if you looked at the spectrum, you'd see that the spacing of the lines is different for this molecule than for this molecule. So if you have a sample of carbon monoxide that happens to contain both, you'll see a blend of the lines that's dependent upon the so-called, what's it called, the isotopic. What's the word for the fraction of the molecules in a given isotope? Isotopic. I'm drawing a blank. But it turns out that if you buy a bottle of carbon monoxide, something like 1% of that carbon monoxide is C13. Or you can't get away from it. It's there. It may be kind of unimportant, but it's there. Okay, now what about non-rigid rotation? We have to be practical now. Remember, B is 1 over R squared. So if you start stretching this thing, now I've got to think about stretching. What value of spacing do I use? As you increase the intensity of the vibration, you can imagine that the average length is going to be different. So as you stretch the vibrations, as you go up in quantum number and you increase the stretching, that was going to lead to an average R that's bigger, which means the B goes down. Or what if you start rotating it faster and faster and faster, so that the quantum number gets higher and higher and higher? The centrifugal distortion pulls this thing apart. And again, that's going to cause B to go down. So as you go from the rigid rotor to the slightly non-rigid rotor, the line spacing changes a little. Not much, a little. That's all it does. So what we do typically is we put in a correction term. So here, the f of j was the term we had, rigid rotor term. Now we put in what's called a centrifugal distortion term, d. That's a correction term. It's not very big, but it's there, and it can be measured. We also recognize that because as you go up in v, that has an impact on b. So we start writing b with a subscript v. So b varies slightly with v, and there's a d term. There's two corrections that come into play, and there turns out these are small numbers. It turns out that d, this is an approximate relationship. For example, d over b for nitric oxide is about 10 to the minus 6. So unless you're being really precise, this is not a big deal. But if you're trying to understand exactly where the line position is, we'll put that in. So the correction to the rigid rotor is the correction for vibrational quantum number and the distortion, rotational distortion. And this depends. Notice that this B over omega will turn out to be the vibrational frequency. So when you have a stiff molecule with a high frequency, this D over B is even smaller. Okay, now I told you D over B is small. What about the vibrational dependence? So the way this is done, B is written with a subscript V. It's an equilibrium value based upon the minimum of the potential energy well, where the internuclear spacing is R sub E, corrected for V, where alpha is a positive constant. So as you go up in V, B goes down slightly. Remember, why does it go down? The average spacing is getting bigger, which means the moment of inertia is bigger, which means that B has to get smaller. So this is a correction term. So if, in fact, I tell you BE and alpha E, you now know B is a function of V. Those are terms that are in books, so you look them up. You look up the numbers that are well known. They don't change with the experiment. They are physical parameters. The Bible for some of this work is written by Gerhard Hertzberg, maybe 60, 70 years ago, Canadian guy. All these things are in the Bible. Here's some examples for nitric oxide, just seeing how where B sub B is 1.7. Alpha, now that's that vibrational correction here, is about 0.01, 0.018 rather. So these are kind of representative numbers. So you'd look these up. If you wanted to calculate, now if you had these numbers, you can calculate what? The positions of the lines. Not the strength of the lines, because that depends upon the populations and the Boltzmann distribution. So there's positions, strengths, and shapes. So this is how we do positions. Now we're going to go to vibration. The reality is, if you measure the, say, the emission spectrum or the absorption spectrum of carbon monoxide using what we would call a Fourier transform infrared spectrometer, FTIR, we would find that these are the lines we find in, these are wave numbers. So this is 4.5 microns. What do you see? You see a bunch of lines in two groups. You're seeing the two branches of the fundamental band of carbon monoxide. There's a gap here, and that's called the null gap. If you look closer, you see, well, there's some other little fuzz in the background. Carbon-13. 1%, say. So we're going to extend our rotation now to include vibration, and we'll enter at the simple harmonic oscillator level, we'll advance to the anharmonic oscillator level, and we'll combine vibration and rotation. So we'll go back to our mechanical model, simple harmonic oscillator. Now we're going to allow it to be oscillating on a frictionless plane. And this is a system, it's an ideal system. So if you take two masses, frictionless spring, perfect spring, you pull it apart and let it go, it'll oscillate forever. It'll oscillate at a certain frequency. What does that frequency depend upon? So if you had a course, and you must have had a course in mechanics or strength of materials, we represent the force law between these two masses with a linear spring that's called Hooke's force law. So here's our molecule. Let's say we compress it to the minimum. So we compress it to one side of that potential energy well, and we let it go. It's going to just sit there and oscillate forever at the instant of greatest compression. So the equilibrium position is the one where it's where the potential energy is zero and the kinetic energy, so it goes back and forth past the minimum. That's RE. So you go from R minimum, there's RE, and then you go to R max. So we start with classical mechanics model, and we only bring in quantum mechanics when we need to. So the linear forcing law is called Hooke's law. It says that the restoring force when you extend a spring is a constant. There's a lot of K's in gas dynamics and kinetic theory and rate constant theory. K is the notation for the forcing law. So this just says the extension of the spring from its neutral position, the restoring force is K times that number. So it's a linear forcing law. And for that system, there's a fundamental frequency of vibration that's independent of how far you extend or compress the spring. You let it go, it only goes at one frequency. It goes like the square root of K over mu. Remember that reduced mass, M1, M2 over the sum. So in units of wave numbers, that's the frequency, this is in hertz, over C. So if you tell me the reduced mass, and I observe this vibrational frequency, I've just determined K. Or you tell me K, I can calculate the frequency. Potential energy for a linear system like this is parabolic. The stored energy is 1/2 K delta R squared. So what does that mean? That means that this is the potential energy of our oscillator, simple harmonic oscillator. Here's the U, that's the potential energy. You can see now we're coming up on the allowed quantum transitions of 0, 1, 2, 3. So if I take this molecule right here and let it go, the potential energy will go down as the kinetic energy goes up and so on. It'll just oscillate back and forth forever. If you pull it apart far enough, it'll eventually become the dissociation energy. Now here's the real molecule. The real molecule is not parabolic. It's steeper on the compression side. As you push those two nuclei together, these electrons start pushing against each other. They're not happy. If you pull it apart, it gets lazier and lazier and lazier, and it'll eventually dissociate. That's the real molecule. Now, quantum mechanics. Quantum mechanics tells us that we'll have a vibrational quantum number, which will be 0, 1, 2, 3, and that the energy will be omega V plus 1/2. That's kind of an interesting thing. So V is 0, 1, 2, 3. This is the vibrational energy. What happens when V is 0? It still has 1/2 omega. That's called the 0-point energy. That's kind of a surprise. That even at low temperatures, this thing has got some energy. Not much. Okay, and now quantum mechanics. So we use the quantum mechanics to give us the energy levels, introduce quantum numbers, and now we have the selection rules. And quantum mechanics tells us, for the harmonic oscillator, that the only allowed transition is 1. Nice. The upper and the lower are always separated by 1. Those are the allowed transitions for a harmonic oscillator. What happens if it's not harmonic? Well, now we got a little more other things can happen. So the harmonic oscillator says that all these spacings are equal, h nu. They're all h nu. They're all the same. Now, anharmonic oscillator. Anharmonic oscillator, we add a couple of terms. So you can add as many as you want. Usually, the first one is called, this is omega E. That would mean we have units of wave numbers now. Omega E plus, this is the correction term. The first correction term is omega E XE. The next one is usually omega E YE. But this is the first correction term. And you can add more. So that's a correction term. What is it showing? As you go up in V, this negative term gets bigger and bigger. So you're reducing the spacing slightly of these transitions. That's the first anharmonic correction. It causes the actual energy spacing to be slightly less as you go up this ladder. They call this the ladder. Now, notation. Spectroscopy is a lot about notation. Delta V is 1, that's called the fundamental band. Delta V is 2, it's called the first overtone. Delta V of 3 is called the second overtone. But the fundamental can be any of the delta V of 1. It can be 0 to 1, 1 to 2, 2 to 3. All of those are fundamentals. All of these are first overtones. So now what about the frequency? So the frequency between 0 and 1 is always just the difference in G. If you go to the anharmonic model, you'll see that here's the correction term for 0 to 1. But now when I go 1 to 2, the correction term is different. So you have to remember, notation. Fundamental is delta V of 1. But the actual frequency depends on the specific vibrational quantum numbers that you're going to do. So there's a slight difference in position for the 1 to 2 and the 0 to 1. That's what happens when you introduce the anharmonicity. That also means you change the selection rules slightly. Back to the partition function. Partition function for an oscillator is, here's the e to the minus energy over kT term. This is the degeneracy term. I didn't say that right. This is the partition function term. The degeneracy for vibrational motion is 1, so that there's no more degeneracy in that term. Now, you have to be careful in these problems where you pick as the zero of energy. If you pick the energy to be 0 at the bottom of the well, then G, I didn't say that right either, excuse me. There's two ways of doing this. Some people pick the 0 at V equals 0. Most people pick 0 at the bottom of the well, but they differ by 1/2 h nu. You have to be careful about this because when you do the Boltzmann fraction, you've got to be consistent between the numerator and the denominator. One of my PhD students spent 5 months tracking down a problem that turned out to be she'd used different 0 of energy in the numerator than the denominator. So just be careful. So if you pick this system here, which is common, if any of you had the book by Vincent and Kruger called Physical Gas Dynamics, for example, they pick it this way. So now this is the form of the partition function. You have to be careful about using the same 0 in the numerator and the denominator. Okay. Vibrational temperature is always Hc over K times the fundamental number. Hc over K is 1.44 omega E. So here's some numbers for oxygen. Here's some of our molecules. Here's the characteristic temperature. So remember, from the rotational temperatures, like oxygen is like 2 degrees. For vibration, it's 1,000 times higher. So the rotational spacing is tiny compared to the vibrational spacing, which is tiny compared to the electronic spacing. So that's why these spectra occur in different regimes. Now here's our chlorine case. Remember, you had this small rotational energy because it's also got a small value of theta because it's a kind of a sloppy molecule. I think we might have more of that later. Here we are. Here's some typical values for some gases we might care about: molecular weight, vibrational frequencies, anharmonicities, constants, so on. Hydrogen is an interesting one. Now, because it's low molecular mass, it has very high vibrational frequencies. Very high vibrational frequencies. So the characteristic vibrational temperature is high, which means that oftentimes the hydrogen is mostly in V equals 0. Bromine is an example, however, which is heavy, heavy, heavy. That leads to a really low vibrational frequency. There's a correlation between these vibrational frequencies and the dissociation energy. Now, we have the same problem. It's either active or inactive. So if it's heteronuclear, it's active. If it's, we call it IR active. If it's homonuclear, it's not IR active. The quantum states exist, but you can't see them unless you use something like Raman spectroscopy. Okay, this is interesting. So the dissociation energy is usually related to this anharmonicity. You can see some pattern here. So if you have weak long bonds, small values of K, like here, you have low frequencies and you have low dissociation energies. Given that I'm still not solved this problem, why don't we take our break now? It's about 10 minutes early. And then, let's see, we probably were supposed to start at 11:15. Let's hope we can start by, say, 11:05 or something like that.